Afternoon, everybody. I think we'll get started. This is going to be number three of the three parts of the NRP talks that we've been having this month. This part, again, is going to be led by Mohammad, and it's going to be talking a little bit about inter-testbed networking with FPGAs and SmartNICs using FABRIC and NRP. Like the previous examples, this is the previous ones are already posted to the YouTube channel and to the Google Drive links that we usually share. If anybody missed any of the previous sections, and if you do have questions during the talk, Mohammed said that it's okay for you to raise your hand and be acknowledged, or just type them into the chat, and we'll make sure that we can answer those questions. So I will turn it over to Mohammed.
All right, welcome back, everybody, and thank you all for listening to me talk. I'm pretty sure at this point you've heard me speaking a lot in the past few weeks, so thank you for bearing with me. Today, I'm going to try to make it as interesting as possible by talking about inter-testbed networking, where users can do networking experiments across different ecosystems and testbed environments with interoperability experiments. This, of course, scales to other ecosystems, but for the sake of this talk, we're going to limit it to the Fabric testbed and the National Research Platform and its Nautilus Kubernetes cluster. Like Jason mentioned, this is part three of a three-part series. The first one was a simple introduction to the National Research Platform. It was on June 27th, and that's the date it was also posted on YouTube. And the second one was ESnet SENSE. If you don't know what that is, we're going to briefly brush over it because it's also part of the experiments we do with the stock today. And it's a L2 quality of service path orchestration, which is very similar between the National Research Platform and the Fabric Testbed. To get started, just a brief recap of what the National Research Platform is and a short brief introduction into what the Fabric Testbed is and some other related factors. So the National Research Platform, as we said in the previous 2 weeks, it's a partnership between now more than 70 institutes. It first started at the Pacific Research Platform and evolved into what is today the National Research Platform. And this is especially highlighted after acknowledging that Moore's law is basically ended and there's a rising demand for cyber infrastructure among researchers and academics. And this is, of course, highlighted with the rise in machine learning, AI nowadays. You see novel architectures. So there's different kinds of hardware that is emerging, like Gen AI cards and IPUs, advanced DPUs, smart architecture and smart hardware that there's rising demand for cyber infrastructure for that sort of hardware where it causes sort of a barrier of entry for the domain scientist and either setting up that hardware or acquiring that hardware or understanding how to use or how to program that hardware and so on and so forth. So that's where NRP comes in to provide one whole ecosystem that essentially runs as a Kubernetes cluster called Nautilus that spans across three continents. But it serves as one ecosystem where users can submit HPC jobs using Kubernetes, can schedule GPU jobs for training, inference, so on. This is especially useful for AI, ML stuff, and as well as web services hosted on NRP for the community, such as we host our own GitLab, we host our own Overleaf, and plenty of tools to provide researchers one whole ecosystem to conduct their research. This is, of course, led in daily operations by us at the San Diego Supercomputer Center at UC San Diego, and our partners at the University of Nebraska at Lincoln, and the Massachusetts Green High Performance Computing Center, MGHPCC. And the cluster itself has been in operation for more than 6 years now. And as we previously mentioned, it provides various storage options as well for persistent storage and data, including CephFS, CERN VMFS, S3, and so on. Plenty of software environments and tools, and plenty of collaboration tools, which is very important, including Jitsi, which is a video conferencing tool, Etherpad, which is a note-taking tool, and so on and so forth. And right now, the numbers are even bigger now. It's more than 440 nodes, more than 1,500 GPUs, more than 50 FPGAs of different kinds, and so BlueField 2 SmartNICs or DPUs, and smart SSDs for programmability and near compute storage. And you can see this map right here that we show if you visit dash.nrp-knowledge.io. And
Mohammed, one quick thing. I think that maybe your screen isn't being shared.
oh, are you seeing anything at all or?
No, when you notice when you were talking about seeing a map, I can't. We can just see you, so you may need to reshare.
Oh, my bad. Let me just see what's going on. Are you seeing my screen right now, or is it?
No, nothing right now.
Let me share. My bad. There we go. Are you able to see my screen right now?
Yep, now we can.
Awesome. So sorry about that. I don't know. I was rambling on without any visual element. Hopefully it's better now. And as I was saying, so this is a map of what the National Research Platform looks like. And blue pins are sites and campuses and institutes where NRP is present. Green pins are for data storage caches, and for the Open Science Grid, which is part of the National Research Platform. And if you want to see the interactive map in real time of the available resources and sites and running experiments, you can visit dash.nrp-knowledge.io. And if you'd like to learn more about the National Research Platform, you can visit nrp.ai. And similarly, another ecosystem that is very helpful for researchers that provides plenty of networking resources in a sandbox environment is FABRIC. And the FABRIC testbed, it's a federated testbed, it's NSF funded. It's short for Fabric is Adaptive Programmable Research Infrastructure for computer science and science applications. What this means is that it provides essentially a CI resource that researchers and education use cases can access, where they can provision network resources and start network topology experiments. They can construct topologies, run experiments. What I mean by a sandboxed environment is an environment where users can break stuff, they can test stuff. It's very experimental. It's not running on the actual commodity internet or some deployment or production network where things can break and that could lead to consequences. Here it's a research environment, and it offers plenty of access to plenty of resources like NICs, SmartNICs, shared NICs, programmable FPGAs, similar to the ones that NRP offers as SmartNICs as well, and other resources. Interestingly, more recently, P4 Tofino switches that users can provision and program. Of course, it's across 29 sites in the United States, across multiple campuses, as well as 4 global sites, including CERN, where both NRP and Fabric coexist as well. And you can learn more about Fabric and how to gain access to it, because that is essentially part of what we're talking about here today. And if you want to do interoperable experiments that include Fabric, you have to be a Fabric user and have an active Fabric project. So if that is something you're interested in, all you have to do is visit whatisfabric.net, and that will give you all the information that you need. And another ecosystem I want to talk about is Pacific Wave, or PACWave for short, which is an internet exchange connecting the United States as well with plenty of international R&E institutes for large-scale data and instruments. And the iGrok node deployments. So the iGrok nodes are 7 nodes that are deployed on the National Research Platform. They're one U servers, each one with a BlueField 2 DPU that has 2 by 100 gigabit per second Ethernet ports. And we use those, of course, for all sorts of AI, HPC applications, as well packet processing and pipelines and telemetry. And the CNIC is the entity that made those nodes available on Nautilus and NRP for our use cases. Similarly, AMPath, which is short for America's Pathway, it's a high performance network that connects our connection point in Florida, developed by the Florida International University, which hosts both NRP nodes as well and also Fabric testbed sites. And the main goal here is to facilitate the connection between the United States and Latin America and the Caribbean and South America. And one thing to note here is on NRP, on Ampath's NRP nodes, we have SN1000 FPGA, which is also fully programmable as a SmartNIC that enables geographically extended WANs that can do experiments with FPGAs and programmable network components and SmartNICs. And now the motivation here for interconnectivity between all those ecosystems, the first thing being the access to specialized resources. So each one of these ecosystems has its own, let me call it the character or specialty. So NRP, for example, has more access to GPUs than the Fabric Testbed does. And the Fabric Testbed has more access to network resources as opposed to NRP. And by being able to run experiments as smoothly as running them in one ecosystem, and by being able to provision them as one environment with quality of service L2 and L3 paths, this means that users can create specialized, can get access to a wider range of resources for their experiments. So the one experiment can get a broader range of resources, whether hardware resources, software resources, or connectivity resources. It also allows for end-to-end path control. So both NRP and the Fabric testbed are spread. If let's say we look at the United States, they're both spread across the United States. We can users have the autonomy to construct their path control for their experiments. So they have more autonomy in constructing the topology. Their data is flowing over, their experiment is being run over, and this allows users, especially when throughput is involved and bandwidth is involved and specialized resources. So let's say one resource is in San Diego, one resource is in Massachusetts. We can we can control the topology of our experiment and how we go from the West Coast to the East Coast and back and forth. And of course, distributed collaboration. One main thing here is that by having that interconnectivity, not only can we interconnect our experiments, but this can lead to a broader range of collaborations between different research groups in hooking their experiments together across different ecosystems without having any barriers. Of course, resilience and redundancy, and having those exchange points like AMPath that have redundant links that connect geographically distant areas. Users are capable of constructing the paths, using the topologies, and making use of those redundant links for high bandwidth data movement, for example, which allows for a broader range of scientific instrument use where, let's say, for the sake of argument, a scientific instrument is in Latin America, and a set of hardware that is used for processing the data from the scientific institutes is anywhere in the United States, uh, or just limiting it to the United States instead of going global, even though both ecosystems go global, is that how we process the data from the scientific instruments, we have more autonomy over that if we can plumb how our data is moving to our endpoints and what our endpoints are. And this leads me to talk about SmartNICs. And for the sake of, so SmartNICs here, we mean smart network interface cards. And network interface cards, for those of you who are not familiar with what network interface cards are, they're the hardware component that connects servers and hosts and nodes to networks. Uh, One example of what is called NICs or smart NICs. So folks might disagree on this point, whether you can consider the ConnectX-6, for example, a smart NIC or a traditional NIC. You can see some sources like Fabric Testbed refers to the ConnectX-6 as smart NICs, so you can, and other resources might refer to them as NICs, so you can see both namings. But essentially, some of the smart NIC resources that are offered, so both the Fabric Testbed and NRP offer ConnectX-6 SmartNICs, in most cases dual port 100 gigabit per second. And some of the features for these cards are support for RDMA, which is remote direct memory access, which is what allows for low latency that is very crucial in artificial intelligence and machine learning workloads, that especially in cases of training and in cases of parallel workloads. And they also support advanced virtualization features, like for example, virtual functions for multi-tenant environments where the same hardware resources is being shared, and some mechanisms either by the same experimenters or by multiple tenants and in experiments and use cases. And um, like we said, dual 100 gigabit per second, that's bidirectional throughput. And one other use case is VPP, which allows for vectorized packet processing. which allows for packet processing on the NIC that makes use of the CPU cores bypassing the kernel. Similarly, DPTK, which is the data plane development kit, is what allows for granular control over the network interface card, also bypassing the kernel, so providing sort of zero copy access to individual packets that also achieves ultra low latency and gives more granular control and a programmable component over any network interface card that supports DPDK. And like we mentioned, the BlueField 2 DPUs or SmartNICs, there's seven of them available on the iGrok node, like we mentioned, and they combine the NIC functionality with them being data processing units to offload tasks like data processing, storage, telemetry, networking, security, and they feature ARM cores on their own, so you're completely both bypassing and offloading from the host system for any custom applications that are of course loaded in the form of Docker containers on the ARM cores. And they're also 100 gigabit per second per port, and they're dual port. And before here, I had an asterisk because NVIDIA announced the data pipeline language system ecosystem, which allows for running P4 on BlueField DPUs. Now, NVIDIA announces that they run on BlueField 3s. We've had some success in running them on BlueField 2s, but I'm not going to make that claim. We're still in testing things, but it looks like, from the looks of it, in our preliminary experiments, is that the BlueField 2s also support P4, but that is yet to be 100% verified. And like we previously mentioned in previous talks, we also have the Alveo U55C FPGAs. These are, of course, available on the National Research Platform. And the Fabric Testbed has the U280 FPGAs, very similar in architecture and almost identical in use cases. And we're gonna get to that more in detail, but just to give you a brief introduction, so FPGA in general is short for Field Programmable Gate Arrays, and field programmable means that they're programmable in the field. So they're programmable in deployment, which means they're reprogrammable, as in the whoever is provisioning the hardware resource has full programmability over their hardware resource in what is called hardware description languages and RTL code. And gate arrays essentially means an array of gates, which means logic gates. So users are programming them on the hardware level to in a circuit-like fashion to achieve that full programmability and reconfigurability. And this allows users to not only write that hardware description language code, but also have environments for other higher level languages. Most importantly, here we're speaking of networking applications as P4, which is something we're going to talk about a little bit, and it allows for per packet processing and custom routing and switching and advanced telemetry functions. And this is right here a picture of the U55C that we're talking about. It's either a Gen 3 by 16 pin card or Gen 4 8 pin, 2 by Gen 4 8 pin, sorry. And it has two QSFP 28 connectors, each are 100 gigabit per second. Now, you might call them Ethernet switches, you might call them Ethernet ports, but they're also anything ports essentially with P4 because P4 allows us to handle arbitrary packets. So they're not protocol dependent in any fashion. They're fully programmable in that sense as SmartNICs. And of course, the difference here between the U55C and the U280 is the memory allocation. The U55C has 16 gigabytes of high bandwidth memory. And if I recall, the U280 is more dependent on uh, I forgot. I think it's DDR4, but I could be wrong. But HBM2 is the main difference between the U55C and the U280. But that is not that relevant in SmartNIC applications for users who are using it on a higher level because they see almost identical performance on both cards. And of course, it's a full height, half length single slot card with a typical power usage of 115 watts. And of course, the U280 has a higher power consumption and it's f full, I think it's double width, full length. I also could be wrong on this one. I'm just going from memory. And the ESnet P4 SmartNIC, I just want to talk about it a little bit. So using the FPGAs, we're able to program them as SmartNICs. And the easiest way to do so is through the tools that are offered by ESnet, which are called the ESnet SmartNIC framework. And essentially, the framework itself is a set of repositories that are publicly available on GitHub. And they're very well documented, and everything in there is completely reproducible given the hardware, which is either the U55C, the U280, and also the U250 and the U200 Alveo cards, which are now AMD Alveo. And what it does is it provides a stack of tools that integrates the tools that are provided by Xilinx for P4 programming, so the Open NIC shell and other tools, with the other very useful tools for network experiments. Like DPDK, which allows us to bypass the kernel and have sort of control over the FPGA from the host, and allows us to write our own C++ applications to add sort of programmability between the host and the SmartNIC. And it also provides command line tools that allow us to interact with the FPGA. So we're not going as granular as writing to registers and reading from registers. We have command line tools that are written by ESnet that read the correct registers, write the correct ones, and we can just simply run commands that get, for example, packet counters or reset the card or turn on a switch or turn off a port, sorry, and things like that. And of course, the whole ecosystem is containerized in the form of Docker Compose, and it's essentially three containers that users get up and running, and they're all set to deploy on the hardware. And of course, the way the setup is made is that it's two distinct workflows. So you have the development workflow, which you can see here on the right side. It's where you write P4, use the ESnet framework, compile the. You can also simulate the behavioral. You can simulate the behavior against PCAP files and hex dumps of packets before compiling, before synthesizing, which is a lengthy process. And you can also have RTL simulation, which shows you a simulation of how the logic is going to run on the hardware with the waveform and latency and other metrics. And after that, you can synthesize, you can get the packaged bit file. And bit file, for those of you who are not familiar with FPGAs, bit file essentially is the logic that we're going to load onto the FPGA to get that P4 programmability with the P4 logic that we wrote. So the end result is the bit file for development, and the input is the P4 code. And we don't need FPGAs present to be able to develop. We just need the Vitis Networking P4 license, which I believe AMD provides for academics through their website. And we have our deployment framework that needs the hardware to be deployed on. And we take our packaged artifacts, which have the bit file from the result of running. It's a make file from the result of running the make file. And also through the ESnet set of tools, we can load it on the hardware, get access to probe counters, get access to all kinds of command line tools, and get access to DPDK, which allows us to send packets to and from the host to the card, uh, bypassing the kernel. Actually, I'm gonna run back to this. So we can treat it as a card that has four ports. Essentially, it's an oversimplification that helps us understand more. So we have packets going in and out from the actual ports and going in and out to the host. That's where DPTK comes in, which allows us to add programmability. And just to elaborate more on that, on the uses of P4 and DPDK in this hardware. So I'm just gonna talk a little bit about P4. And for those of you who don't know what P4 is, even though the name is a little bit not long, but the main goal of P4 is to be very easy to write and sort of hardware and protocol independent. So P4 is short for programmable protocol independent packet processors. So essentially what you're writing is a pipeline that processes packets. That's how you do the smart network functionalities, is in how you process every single packet that goes through the network. And it's, of course, like we mentioned, it's protocol independent, which means you can write your own arbitrary protocols. You can test with different protocols, completely programmable. It's not, let's say, an Ethernet or InfiniBand card, or it's not bound by IPv4 versus IPv6 or TCP versus UDP. It's not bound by any of that. It's bound by what you define in your logic. And of course, it's a C style language. And it's, like we said, hardware or target independent, which means the language itself is made so it's very consistent across multiple hardware platforms. And most, if you've heard of P4, most likely you've heard of P4 on Tofino switches. But whether it's any ASICs like Tofinos or FPGAs or SmartNICs or DPUs, the code itself is very similar with the small differences between different architectures. Um, and that's one of the main goals. And of course, one of the main use cases is, like we said, telemetry as well as packet processing. The way it works is through, we can call them three blocks, which are the parser, the match action pipeline, and the deparser. So the parser is how we define the logic that does the packet processing for the ingress packet. So the packet going in, we have the match action pipeline where we do all the logic for how the packet is processed after parsing the headers and add all the control plane, all the stateful externs and so on. And deparser is also how we deparse before egressing the packet. And I know this is not a talk on P4, and I don't want to make it too technical to the point of being sort of steering off the point. I just want to show you a brief example of a P4 program. So this is actually a full P4 program. And the idea is not to go deeply into P4, but just to show you how easy it is to get up and started with P4. So you can see we're actually defining headers by hand. So I'm specifying Ethernet to have a 48-bit destination address, so MAC address, 48-bit source address, 16-bit Ethernet, Ether type for whatever's encapsulated next, and I'm defining what IPv4 is as just source and destination. And I'm setting my headers to be Ethernet and IPv4. And as you can see here, there's room for doing arbitrary stuff. There's room for malformingly defined stuff and malformingly egress packets. Of course, that's not the point, but the point is to have full programmability, which is the point here in having just an IPv4 that is to just source and destination address. And you can see here we have our logic, how we're parsing the headers, so we're extracting the Ethernet. Then based on the value of the Ether type, we're either extracting the IPv4 or we're not extracting it as a header. So my idea here is to parse the headers, not the payload. So we get to define the distinction between what is header and what is payload and how we define our headers. And we have match action pipelines where we have table lookups. You can see here we're doing our IPv4 destination address lookup, and we're eventually egressing the packets, also choosing what we emit, so what we include as headers in the egress packet as well. So one key application you can see here in P4 is that, for example, NAT applications, because you can, between ingress and egress, you can parse IPv4 and ingress and emit IPv6 and egress, for example. And the other thing here to talk about with P4 is something that goes in conjunction to make very powerful workflows is DPDK, which is short for the Data Plane Development Kit. And if you want to learn more about DPDK and how to install it, you can just visit dpdk.org. Plenty of hardware like the ConnectX 6 cards we talked about has upstreamed the drivers for DPDK, so it's very easy to install and run DPDK on that sort of hardware, and it's very easy to install and run it on FPGA SmartNICs as well, courtesy with the tools courtesy of ESnet and the ESnet SmartNIC team. And DPDK allows us to, like we said, bypass the kernel to connect to the NIC, and gives us access to the packets with zero copy from the user space. We can write our own applications or use available applications, such as, for example, packet gen, which is a tool that allows us to generate packets, send them from the host, bypass the kernel to the NIC, and then our NIC can act sort of as a gate to the outside world where we can have our C++ logic or our packet gen commands send packets to the NIC, then for in the case of FPGAs, send packets to the NICs, go through the P4 logic, and then egress to the outside world or egress back to the host itself. And that is, of course, determined by the P4 logic and the control plane it uses, and of course, overridden by the SNCLI tools, so the SmartNIC command line tools that ESnet provides, which allow us for granular control where we can control egress in, for example, sandboxed environments where we want to egress all packets to the host for the sake of testing. And this is sort of a small figure that basically sums it all up. So we write our P4 code with the ESnet SmartNIC tools. We have the bit file, which we use the same tools to load onto the FPGAs and get access to all the tools. So after it's on the FPGAs, we can, in an oversimplification, we can look at it as a card with four ports, two going to the network and two going to the host. And through the network, we go with our P4 logic and our command line tools. And to the host, we also have DPDK. So with DPDK, we can send packets back and forth between the FPGA and host with, let me call it programmability. And of course, if you have any questions, just feel free to unmute and ask, because I'm not seeing the Zoom screen on my screen. So if anybody raises their hand or anything, I'm not going to see it. So feel free to just unmute and ask whenever you have any question. Uh,
No questions yet.
Perfect. And so with having the FPGAs as programmable network components and many other components on the two ecosystems, now how do we plumb them together? And that's where ESnet Sense comes in. And that was the bulk of our talk last week about the ESnet Sense orchestrator. And Sense is short for software defined network for end-to-end network science at exascale. Essentially, in an oversimplification, it allows us to provision L2 and L3 paths across many endpoints through an API that is intent-based and allows us to set the specific VLAN tags to plumb the paths over and set the endpoints and the bandwidth that we have quality of service for. And the folks from the ESnet Sense team have shared a tutorial that is in the slides if you want to scan it or watch it. This is the web interface for the orchestrator that shows how to start paths with the web interface. And of course, paths that are started with the sense connect to multiple endpoints that connect between that include plenty of National Research Platform endpoints and FABRIC testbed endpoints. And we can use the National Research Platform for our network experiments by using Sense and Multis. So Sense provisions the paths over VLANs, and Multis is a container network interface plugin that allows us to attach interfaces to pods. So the actual network interfaces that are on the host OS, we can just attach them with Multis to show up on the user pods that are essentially pod in Kubernetes, the smallest unit that runs a container. So you can say we can attach our interfaces to containers using Multis. And by that, we connect to the endpoints in these topologies. So here we have ESNet's topology on the upper left hand, and we have Internet 2's topology on the upper right hand, and we have the Fabric testbed and NRP at the bottom. And the orchestrator allows us to connect to endpoints that are available on these networks, these backbones, and these testbeds, and it allows us to conduct our experiments with that fashion. With NRP, we have the nodes that are connected to NRP, and with Fabric, we have what is called facility ports that I'm going to show you a hands-on example of using and provisioning over. And for NRP users, we're in the process of developing a web interface, a web service for provisioning sense paths. So it's oversimplified for users where users can have a drop-down menu to select an endpoint and a drop-down menu to select the other endpoints, whether on NRP or between NRP and Fabric or other environments like Cloud Lab or Chameleon Cloud. And this will start a path for them, either by them specifying a VLAN or them leaving it empty and getting a VLAN assigned to them by the orchestrator. And of course, if you'd like to have access to the operator. Of course, it's still in development, so we have sort of early access for testing. If anybody feels like trying to test the operator for NRP, please feel free to fill the short form on this link. So it's tinyurl.com/seam NRP. Seam is the name of the code name of the project that is all about interconnectivity between NRP and Fabric, which is the operator that also will have hooks to auto attach network interfaces. So users the end goal is to have users have a GUI, click a bunch of buttons, and have your experiment with your topology up and running. And this is what leads us to having interconnectivity experiments. Of course, just a brief couple of examples that I'm gonna just brush over and how we used the ESnet SENSE orchestrator and NRP and FABRIC for some experiments. So just very briefly, one of our experiments was doing SRv6, which is segment routing with IPv6 on NRP and FABRIC by essentially this is how we define the packets. It's per the RFC. Essentially, what segment routing is that we can specify the path that the packets traverse by explicitly setting the segment IDs in the packet headers and in the header definition, instead of relying on routing, and we implemented SRv6 and we implemented microSID SRv6. So microSID SRv6, the different main difference here, up to this point, the packets look almost identical. We know it's an SRv6 packet by it being an IPv6 packet that has a segment routing header. And similar for both ends, but for microSID SRv6, instead of each IPv6 address occupying 16 bytes or 128 bits, you can press them all into one 128-bit field, which is it, of course, how you divide it is basically since it's P4, it's fully programmable. That is up to us, but we divided it according to, if I believe Cisco's white pages, to have 8 addresses in each microsegment being 1/8 of an IPv6 address. And another example of what we did with that more recently is also start an experiment that goes from NRP and Fabric through the sites that have FPGAs to do a similar experiment with encapsulation. So our SRv6 packet is so whatever packet comes in, we're encapsulating that in segment routing. So the original packet you can see here. So this is our packet. We're ditching the payload and taking the rest of the headers and encapsulating them in an SRv6 packet that is traversing the network. And at each segment that has an FPGA that we're traversing over, we're sort of injecting a timestamp from the FPGA, which allows for nanosecond order timestamping. And this is, of course, for the sake of demonstration of capabilities of what is possible with the FPGAs. And just a quick few links to have them in the slides if anybody wants to learn more about how to use the FPGAs. So we've recorded many tutorials and multiple documentations on how to program the FPGAs step by step, assuming you know nothing but P4, which is also very easy to learn. And the examples are fully reproducible. We have a tutorial that we did recently, a few months ago, that is available on YouTube now. And we have our documentation for the National Research Platform with a reproducible example, as well as a Fabric playlist on provisioning FPGAs from A to Z on Fabric specifically, and an NRP one that also explains how to provision FPGAs and do all the SmartNIC tool stacks from A to Z and A to Z. And of course, for a brief hands-on demo, we've created a repo, so it's github.com/nrp-nautilus. It's Joule 18 CI launch tutorial. And I'm just gonna quickly go over the demo with everybody. I hope everybody can see my screen. All right. So just to quickly show you, so first thing I want to show you very briefly is coder.nrp-nautilus.io. So this is the Coder platform, which allows for a graphical user interface and access point into the National Research Platform. It offers what is called templates, which are, as the name entails, templates on how to access the National Research Platform. And one of them is called ESnet FPGA SmartNICs. If you create a workspace, you can name it, specify CPU cores, and specify which node you land on. Essentially, what this starts is a full Kubernetes pod that has Ubuntu installed, has no VNC, right, desktop environment, and has the FPGAs on the pod, attached to the pod, with access to Vivado and the floating license server that we host, and gives users the ready to use access onto FPGAs on the National Research Platform. And of course, we have also the Fabric testbed provides examples on how to provision FPGAs from the Fabric site. This is the Fabric testbed. If you visit Fabric testbed, fabric-testbed.net, this is the testbed. If we go on to Jupyter Hub, which is the access point for the Fabric testbed. Of course, to be able to follow along with this tutorial, you will need to have access to Fabric and have an active project. So if you visit experiments, sorry, I'm not, let me log in. Let's try that again. All right, here we go. So if you visit experiments, you can see I have an active project that is called UCSD-Fabric. So I'm able to run experiments with that. And of course, this is our GitHub repo. Sorry, this is the wrong one. So this is our GitHub repository. It has the notebook we're following. This is public. You can go to the link and download the notebook, and you have a reproducible example that goes through Fabric and Nautilus. And we're just going to follow it very briefly. Let me just see. So slices are running experiments essentially. And I'm just going to delete my slice to be able to start a new one. And of course, we tried to make this as detailed as possible for you to know how to join NRP and Fabric and how to run the experiments. For the sake of this experiment, we're using a namespace on Nautilus, a Kubernetes namespace that is called Seam that we have specified for experiments. And in following this notebook for the next 24 hours, you can access NRP through running the exact identical commands that we're running through what we call a service account token. So a service account token, which we pass down in trying to look for it, which we pass down here. This token is valid for the next 24 hours, and it allows you to use the National Research Platform without actually having credentials and also similar to an active project without having an active namespace. But the Fabric part will still need an account. And what we're doing here in the experiment is, first of all, we're installing Kubernetes, the Python Kubernetes library to be able to use NRP through Kubernetes, through Python, sorry. And we're just importing a few libraries. And you can see here, we're using from Fabric testbed extensions.fablib.fablib. We're importing something called the FabLib Manager. So Fabric library, the Fabric testbed and the developers behind it have provided a Python library to interact with the Fabric testbed. So you can think of everything in the scope of objects and classes, and it's an easier way than running commands and complex recipes to launch simple experiments. It allows you to interact with provisioning VMs. Essentially, what you're running with the Fabric testbed is virtual machines. What you're running with the National Research Platform is Kubernetes pods. So we're using FabLib. You can see it shows me details about my project, shows me the project name and the version of FabLib that we're running. And site is the Fabric site that I'm going to be using. Again, if we go to the Fabric portal, you can look at resource overview, and you can see here different sites. You can see UCSD, for example, has one FPGA, and that is something consistent across the Fabric testbed, is that every site has one FPGA, as you can see, as well as plenty of shared NIC interfaces, plenty of SmartNIC resources, NVMe, GPUs, memory, and disk through either persistent or ephemeral, and CPU cores. In our experiment, we're just using a basic NIC because we're not doing anything fancy, and we're using UCSD for the obvious reason being that both the Fabric UCSD site, which is at the San Diego Supercomputer Center, and NRP resources, they very heavily overlap at UCSD because plenty of the National Research Platform's resources are at UCSD. And we're running a command to generate a slice name. And a slice in Fabric terminology, a slice is an experiment, and a node is so a slice is an experiment and a node is a VM. So you can see here with our slice, we're creating a slice and then we're specifying parameters for our node. So you can see here, image is a Docker Ubuntu 20, so that's 2004. Facility port. So facility ports is what Fabric calls the ports that connect to facilities, as the name entails, the ports that connect to other institutes, other connection points. And what that essentially translates to is that facility ports are endpoints on the Sense orchestrator, and users can use that to connect to NRP as well as other environments. And we've linked here if you want to learn more about facility ports. This is a talk that was previously given about Fabric facility ports. And if you want to learn more about the Sense orchestrator, there's also a video tutorial as well as the Sense website. But here we're using the facility port called, let me find it. So facility port is called FP1-UCSD. I'm just looking for where we defined it. So let me scroll down here. You can see this is the name of the facility port that we're using that connects Fabric to UCSD and essentially NRP. And we're using VLAN choice here. We're using 3110. 3110 is a VLAN tag that we set up for this experiment, and we use the sensor orchestrator to have a 10 gigabit per second link over the facility port to one of NRP's nodes. And we're adding a basic NIC that uses the facility port. And we're starting our experiment. I'm just going to show you here. So we're adding the interfaces to the network and submitting the slice. And this, of course, takes a few minutes because it's doing a lot of things under the hood. It's communicating to get to see if the resources are available, to see if the network resources are available, and to provision everything. You can see here it's in configuring, it's ticketed, it's going to take a little bit to start. You can see here we go on to experiments, my slices. It shows up here as configuring. You can see here, this is node 1, this is my VM, and I have a NIC that is connected to the facility port, and facility port is connected to the VLAN on the facility port FP1 UCSD, which means essentially from the Fabric side, this is the black box. Since we are using the orchestrator, we plumb it to something. And in our case, that something is the Fabric testbed. Just show you how that looks from the Sense side. So this is the actual orchestrator and not our operator. You can see this is the facility port and we're connecting it to node-2-8 on NRP, and node-2-8 also has both FPGAs and network interface cards. And just gonna give it some time while it starts. I'm just gonna explain the cells and bits that we're gonna be running. So essentially we're setting up 192.168.1.1 to be the IP address of the interface that has the facility port, and we're installing ping. And similarly on the Kubernetes side, we're specifying our namespace to be seam. We're creating a pod name, and we're using the token we talked about, and we're checking for connectivity. And then first thing is we're defining a network attachment definition that is called my-VLAN-3110. If you'd like to learn more about this, we explained this more in detail last week, and we're using the same VLAN connected to the facility port. And the network attachment definition, of course, in its essence, it's not related to the node. It defines what the host interface that we're using is called. And then when we apply our pod here, you can see, so here we're submitting the network attachment definition. we're specifying node to be node-2-8. And when we apply our pod, so this is our node affinity. When we apply our pod, we're explicitly telling it to land on this node because the network attachment definition by itself doesn't say this node. So that's one thing to be careful for because you might try to start the pod on a node that does not have the interface that you're looking for. Then Multis will have error logs. And of course, we add network capabilities to our pod, which are essentially system capabilities that allow us to use ping from within a Kubernetes pod, because that is something that is not allowed by default. And then we start our container in the pod, which in our case is just using Alpine and sleeping for an hour for us to do our experiment. I'm just going to check on this. It's still configuring. Hopefully, it'll finish in time for us to run our experiment. And after our pod is up, after our slice is up, uh, uh, after we submit it, here we're submitting it, creating the pod, reading to see if the pod has been created. And similarly, we're looking at the address for the interface. As you can see here, since it's already up, since it's already there for output from the previous run, I'm just going to show you, for example, this has an IP address. We configure our own IP address to be for that same interface. And now it's 192.168.1.2. And then we can ping from one to the other. So this is from Nautilus to Fabric. We're pinging at 192.168.1.1. And the other way around, from Fabric to the Nautilus, we're also pinging same command, but here we're using the Kubernetes Python library to execute it. Here we're using Fabric's FabLib. And of course, it doesn't have to be through Python. This slice.get nodes, and since our experiment get nodes is a list, our experiment has one node. So one Fabric VM, we specify index 0, get SSH command. In Fabric, we can copy this command and paste it in the terminal, and that'll SSH me in. Of course, we have to run a fresh one to get the fresh IP after it starts. Similarly, in the Kubernetes library, we can specify a kubectl exec command that goes into the pod, and we've given you a cell where you can run it and just get a kube exec command that you can run anywhere that has kubectl installed. So you can either install it in the you can either install it in the Fabric terminal or you can install it locally. Paste this command from wherever because it's using the token, doesn't need any authentication, and then you'll be inside your pod. All right, it's active now. It's running boost the post boot config script. Let me run everything real quick. I know we're running short on time, so hopefully we'll get everything up and running. And all right, here we go. So this run, you can see here, 196, 168.1.1. This is from this run. Now we're installing ping. Ping is installed. My pod name is my pod QNF ZNH. We have our terminal. We can look. This is called K9S, which is a tool that allows us to access the cube command line tools in a easy to observe and easy to control fashion. This is our pod. You can see it's been running for the past 26, or it was admitted 28 seconds ago. And using the token, here you can also pass a kube config file if you're an NRP user to use the script. You can see here, exception here because it already exists. So if I look at my network attachment definitions, you can see my VLAN, I created it 15 hours ago. That's why this is complaining. And I'm specifying node-2-8 for node. And here, the pod definitions as we talked about, it's running. And we set this is the original IP address. We set it up as this address. And we're pinging from Nautilus to Fabric and from Fabric to Nautilus. All is successful. Now this is our fresh command here. So this is my Fabric slice. And you can see I'm inside Ubuntu on the Fabric VM that is connected. And NF config, show me the interface. This is the interface that is correct directly connected to my Nautilus experiment or pod. Similarly, I can paste this link. So let me go. I have kubectl installed. I can just run this, and now I'm inside my Alpine container. And you can see here also net1 is my interface, and the two are connected to each other. And we can, since we're in Kubernetes pods and Fabric slices, we can add more resources if our experiments, let's say, have GPUs, have different networking components, and go on from here. And of course, for cleanup, we can delete the slice on Fabric, and this will show it as terminating, and then delete. And similarly, the Kubernetes pod, we can either explicitly delete it, or since it has the sleep for an hour, so 3600, it'll be done in an hour, or we can just Control D and delete it. And sorry, we're almost out of time. I'm just gonna stop here and see if anybody has any questions. I'm more than happy to answer.
Thank you for going through all of that. I don't see any questions in the chat room, but if anybody does want to raise their hand or just ask a question, we can certainly answer them in the couple minutes we have left.
All right. One thing to mention is please feel free to join the NRP community, to join our Matrix chat, and just join our community and ask us any questions that you like to ask, and use NRP's resources, and reach out to us with any questions, anything you have, any feedback.
All right. Well, thank you so much for going through all of this and going through the previous versions as well. We'll make sure that we get this one posted along with those. So if you can just send me the slides, I'll make sure that those go up along with the video. And we will be off for a couple of weeks. Our next talk will be on August 8th, and that'll be a Personar office hours session. So hope everybody has a good couple of weeks off, and we'll talk to everybody soon.
Awesome. Thank you all.